Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, we know that CFD or computational fluid dynamics plays a very important role for design and analysis of complex mechanical or civil engineering problems. Not only mechanical engineering, civil engineering, it is for daily lives also. We can get a lot of ideas for design and analysis of different complex things, right? So what it is done in CFD analysis, we can see or we can visualize the behavior of fluid particles inside any intricate objects or any shape, and by visualizing their behavior, maybe profile, velocity profile, or temperature, pressure, etc., we can design and analyze the product through which it will be utilized, right? So in this case today we'll be analyzing a basic problem. It will be mixing of two different fluids inside a pipe, and it is having two different ends. From these two ends, a different fluids will be entering, and we'll follow their behavior, the velocity profile, their temperature profile, velocity, temperature gradient, etc. We'll see, and based on that we'll try to analyze the fluid behavior, and we can design the pipe accordingly, right? So we'll start this one right now using SolidWorks. Okay, we'll start from front plane, normal to, starting from sketch, then line. Okay, let's take a line, then another horizontal line. Let's provide smart dimension to this one. This one 100 millimeter, and this one also 100 millimeter. Okay, let's get the angle in between them equal to 130 degree. Okay, drawing is complete. We will exit from the sketch and select sketch again, and from the features we'll go for swept boss base, and we'll provide a circular area at the beginning. So pipe is ready, right? Now let's provide diameter to this one. Let's get this diameter equal to 30 millimeter. Okay, right. Now see the different planes. This is the top plane, the right plane. So on the right plane we can draw another circle, normal to, normal to. That's how we have to draw. Here we have to draw a circle. So we want to get the center line. You can get from the center line again. Again, line will be equal center line. Okay, now let's draw the circle. Okay, done. Exit from the sketch, and we will select the sketch again, then extrude boss base. Features, extrude boss base. We want in the reverse direction, so change the direction, and length of extrusion will take near about 100 millimeter. Done. Drawing is complete. Next part, we have to remove material from all these ends. We can do one thing easier version is shell. Click shell and select all surfaces. By control, select the surfaces. All surfaces selected, and the thickness of this one, shell thickness, we will provide 2 millimeter. Okay, done. The drawing is complete. Now see whether the drawing is perfect or not. To see that one, we can make half segment of that one. Okay, let's see. It's perfect. No problem in the drawing. You can see the interface, the in between junction, It is perfect, no problem with the drawing. So we'll make it complete drawing again. Right. See, before starting this CFD analysis, we have to do some operations like we have to make some end should be closed. We want to provide some leads at this closed end because we want to generate closed volume, right? So we have to make some leads. It should be provided from here. It can be done from tools, create leads. We make 3 leads. This is number 1 lead. That's number 1, number 2, and number 3. Yeah, right. We got 3 leads. Green check. The leads are made. Okay. Next part is through this pipe, the fluid particles, massless particles will be moving freely. So, if you want to visualize them properly, it should be should transparent, right? To make it transparent, select the subjects. Then change transparency. This is transparent right now. Again, inner part we have to make transparent. Again, select this part. Again, change transparency. It is perfect. It is transparent right now, right? Okay, fine. Now it is ready for CFD analysis. Before going for analysis, we have to save the model. Save it by the name of pipe. Okay, save it. Now, while opening the environment of CFD analysis, we have to start with wizard. The project name we can provide as mixed flow. Okay, done. Next we have to select the unit. Default, a lot of systems units are CGS, FPS, IPS, but we will take default like SI system. Next, it is an internal analysis type. So we will click internal, and next we have to select the liquid or fluid. So we are selecting 2 fluids. Maybe you'll see what are the different fluids available. Here having acetone, ammonia, a lot of fluids are there. Better to take water, and some other fluid maybe we'll take acetone, right? Acetone. 2 fluid you have taken, acetone and water. Okay. The next, we don't know we don't want this roughness parameters and things, and also default thermal conditions we don't want. So next, this part of concentration, that means how much percentage of water and how much percentage of acetone should be mixed. That one will provide during applying boundary conditions. At this moment we don't require this, and relative parameters is not required. So finish. Now this is showing computational domain, right? So all the objects should be inside that one. Now we can, if some part is outside, that will not be perfect one. So better to take all parts inside this computational domain. What to do is drag those parts which we feel that is outside. This one also can be little dragged on this side. Now the whole object is within computational domain, right? This whole object is there. Now we have to make this one hidden. We have to make this one hidden. Okay, ready for analysis. Now very important thing is next part we have to apply boundary conditions. While applying boundary conditions, it is better to take the segmented. We'll take half of this one. Okay, half of this is ready. I will apply boundary conditions. Insert boundary conditions. It's coming like that. Now first we'll take inlet mass flow rate. It is 0.301 kg per second, and what we are putting, that will be checked from substance concentration. Here water and acetone both are available. What we'll do is from the top pipe segment, will allow water to pass only. So it will be having 100% water. Water consuming 100% and no acetone will be there. So acetone is 0. We are taking at this level. Okay. Yeah. Next part, here we have to put acetone, right? Again another boundary condition is required. Insert boundary condition. What is required? We have to put inlet mass flow rate. Now substance concentration. We'll see in the top segment of the pipe we have provided water, and down segment we can provide acetone also and mixed of water also, right? Let's provide 50% of water and 50% of acetone from here, right? If you like, you can provide only acetone also. That is not an issue. You can provide 30% of water and 70% of acetone also, or 10% of water or 90% of acetone also. That is not an issue at all. Let's take 50% of water and 50% of acetone from this end. Okay, selected. Now last boundary condition we have to apply atmospheric pressure at the exit end. So it will come from boundary condition again. Insert boundary condition, so we should apply pressure. It will be atmospheric pressure. So select that, press OK. All boundary conditions we have applied. Now let's consider the whole segment of the object, the pipe, right? Whole pipe is there. Next part, we have to select some goals. Insert some goals. A lot of goals are there, like global goals, point goals, surface goals, etc., right? And equation goals. We'll take global goals first. Insert global goals. Our aim is to see velocity profile while the water or this acetone will be flowing throughout this pipe. We'll check velocity profile. So we'll see average velocity. Okay, this is one goal. You can check another surface goal. Surface, want to see the surface pressure, velocity, etc. So we'll select average velocity. You can select average pressure also. That one we'll select on. Okay. So velocity is equal at which end? We have to select that end, right? We'll select velocity profile at this end or that end. Okay, we'll select this part. Select other. Press OK. Next one, we will have to run this program. We have to run this solution. Let's run it. While it is running, it is very important to see the solver window. From the solver window, we can get some idea like what is going on inside actually. How the velocity profile, pressure gradient, temperature gradient is changing. You can see. You can actually visualize from this window. Okay, it is showing it is ready for calculation. Now it will start calculation. Number iteration number 3 is already started. It is showing pressure distribution throughout the pipe. From left side to right, the pressure distribution is showing. You can see at the left side, pressure at the exit entry is very high, and that is moving at the junction of sink. From there only, pressure is reducing, and at the exit, pressure is very less, is equal to atmospheric pressure. Already 25 numbers of iterations is over. Let's see some other profiles. From setting, we can check velocity profile also. Okay. Here also from the velocity profile, see at the beginning velocity is normal, but at the junction where two fluids are mixing, from their velocity is very high. Another thing we see that before entering that junction, at the boundary level, velocity is very less. Velocity is almost zero at the boundary level. In both entry level, velocity you can see at the boundary level velocity is zero. But while mixing, the velocity at the boundary is increasing again, and maximum velocity is after mixing. So some turbulent flow we can observe here after mixing. Right? To see another thing, maybe you will check temperature distribution also. Okay, temperature distribution, it is having now not that much of variation, is almost same. It's not changing at all temperature. Solver is finished, so we can go for the results right now. It is ready. Let's see the results. First of all, we have to see the cut plots. You have to see the cut plots. It is the variation of temperature, pressure, velocity, etc. along a certain plane. We can take front plane will be better one. Along front plane we want to see velocity, pressure, etc. Insert the cut plot. Along this front plane we'll see what we want to see. We want to see pressure and velocity, right? Let's see velocity. Okay. This is the thing, right? But for better viewing, we can see the front view. Okay. Now we can analyze a little bit. Let's see. At the entry, velocity was in the range of 2.327 into 10 to the minus 4 meter per second. And if you see at the boundary level also, it is blue color. That means velocity is 0. Before mixing, velocity at both the ends was 0 meter per second. Boundary level, it should be 0 velocity, of course, because of drag force, right? And again, velocity is increasing at the mixture when two fluids are mixing. At this point, velocity is equal to 5.429 10 to the minus 4 meter per second, and then it is increasing. The highest point, the highest value is 7.7 into 10 to the minus 4 meter per second. This velocity is very high here, right? Okay. Now let's see another thing. Temperature distribution. We'll see again. Temperature distribution, again, no variation. We'll see pressure also, no variation, right? Along that plane, pressure is not changing at all, right? Okay. What we'll do is we'll remove that part from cut plot, clear and hide. Now we want to see surface plots. Insert surface plots. All surfaces will see. When you see pressure, velocity, first of all see like the velocity. Okay. So it is the velocity throughout the external surface, right? You can see all surface, it is velocity is 0. At boundary layer, velocity is 0. Now if you see the front side, you can see velocity at the innermost part is maximum. Velocity at the outermost part, it is 0. Then it is increasing to 7.7 10 to the minus 5 meter per second. Then finally it is coming in the green layer, that means 4.65 10 to the minus 4. Then yellow level, then finally it is coming to red level. That is at the mid level, velocity is very, very high, you can see, right? Okay. Now we see another thing like pressure distribution. Let's see how much it is. Again, pressure distribution, you can see throughout it is same. There is green line. Green color is indicating pressure is 101.325 Pascal. That is atmospheric pressure. It is. Pressure is not changing at all. Pressure is almost same throughout the section, right? Okay. Next part, very important part, we have to see the flow trajectories. That is, fine massless particles will be moving throughout this pipe. We can visualize their movement and their behavior, their flow, their temperature gradient, velocity gradient, etc. We can see, right? So insert flow trajectories. Before that, we want to remove this part. What is there? Before that, we want to remove this part. So what we'll do is cut plots, surface plots, we'll remove it, clear and hide. Next one, we remove starting with flow trajectories. Insert flow trajectory. Instead of 20, we'll take 40 numbers, and instead of pipes, the pattern will be arrows. Okay. What we want to do? We want to see velocity gradient throughout this pipe. You select velocity. Okay. Now what we want to do? We want to see velocity at from both the ends, right? Select other. Okay, this is selected then. Then here again, select other lid. Both the lids have been selected, right? Okay, fine. Okay, check. You can see velocity profile developed. Next part, also we will animate this one. That will be showing better way. Clear and hide, and then animate. Play. See, it's very smooth flow. We can see at the beginning, both the pipes ends, flow is very smooth. Let's see the front view. We can analyze, see some plane, you can see here some dead points are there, some dead points at boundary level, velocity 0. Boundary level, no movement at all, velocity 0. But you see, after mixing, the fluid particles are moving towards the boundary. That means velocity is not 0 at this end, right? And here also, after mixing, the velocity profile is changing. Value is also changing. Initial velocity was 0 to 7.7 10 to the power minus 5 meter per second. And at the mixture point, when two fluids are mixing, you can see the velocity color is changing. That means it is in the range of red color. That is 7.75 into 10 to the minus 4 meter per second. And also, design is not perfect. You can see here at this end, it could be provided some kind of delay that interruption should not be there. It should be smooth flow. We could see. So this design should be changed a little bit. Again, if we could have made this a little bit more, this angle should be made a little bit lesser. Then in that case, the flow would be more smooth, right? You can see velocity at the mixing is very turbulent. The velocity is high. Now you see the pressure distribution. Pressure distribution is also, pressure distribution is showing nothing. It is almost similar, no change at all. Let's see the mass flow rate, mass fraction of water. Let's see. Mass fraction of water is 0.5 to 100%. From top level, we can see water is flowing, and from down level, we are having mixture of water and acetone. Again, it is very clearly seen at the entry point in both cases. At the boundary level, velocity, at the boundary layer, velocity is 0, and after mixing, it is moving with high velocity. Even at the boundary layer also, velocity is very high. Now we'll move on to fraction of acetone. Acetone and water mixture is passing to the bottom one, and from top one, water is passing, right? So acetone is 0 to 50%. Okay. Next part is very important part. We want to see the actual flow of these massless particles in the form of injection, right? It will be coming from particle studies. We want to see the massless particles, the behavior of massless particles, actual view to be seen. You go to the particle positions, flow project trajectories, and clear and hide. These are not there. Now we'll start the next part, particle studies. You start from wizard. Next. Then we have to select the surfaces from where we want to put or inject water. From this top pipe, we have to inject water. Lead is selected, right? From lead, what we are injecting? We are injecting water from the lead. Okay. Done. Now again, from this end, we have to inject something else. So we come from injection again. Insert injection. Select other. We want to inject acetone from here. Okay. The injection is done. Next one, we have to run this. We have to run this particle study. Okay, fine. Next one is see the injection of both these particles together. Play all. Yeah, it's showing very nicely. From down we can see it's a mixture of acetone and water, and from top we are having mixture of water only water is passing to the top one. This is very smooth flow is there, and again you can see the all things what we saw before at the mixture point where the two fluids are mixing. Some turbulence is created there, and you can see the different parameters like velocity profile, etc. Velocity, you can check velocity. This is velocity profile. We have already analyzed this one. That means velocity at the exit point, it is very high. It is 5. It is 7.7 10 to the minus 4 meter per second. After the mixing, only velocity is becoming high. Even at the boundary layer also, velocity is very high. Boundary layer also velocity not 0. It should be 0, but after mixing the velocity at the boundary layer, it is in the level of 3.1 and 10 to the minus 4 meter per second. Right? Now we can do one thing. We can generate a report based on all this behavior of fluids, even its velocity gradient, pressure gradient, temperature, mass fraction, volume fraction, etc. can be seen in the report. We can generate a report in the Microsoft Office. File, create a report. Report can be generated from a template. Let's take the template flow simulation report. The report is already generated. You can see the report. It is like SolidWorks flow simulation project report. It is having all the details like objective analysis, environment, model information, everything is there. Even like result analysis also, boundary conditions provided, goals, global goals, etc. everything is there, and result analysis, result values, goals, etc. already provided, right? And also if you like, you want to input those drawings also, the sketches, different graphs can be plotted from there, that can be imported here, right? Okay, so this is all about, this is the basics of CFD analysis to a simple model. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again.